In learning about equilibrium regarding the solubility of a substance, we have now studied this concept of molar solubility, or to what extent does an insoluble substance break up in water. And so what we want to do is that oftentimes when we discuss this idea of does a substance dissociate, in other words, does it dissolve or does it not dissolve, one of the most important things that usually gets kind of lumped into this is this idea of, is a solution saturated or is a solution unsaturated? And so you've heard those terms before, but what we're going to do is that in this episode, we're going to apply this concept of saturation to an equilibrium expression or to our solubility product equilibrium understanding. So, in a nutshell, here's what it means. A saturated solution is any solution that has achieved equilibrium. That's it. It's any solution that contains enough of the ions floating around in the solution such that we cannot add any more ions into that solution because the solution can't hold any more of those particular ions. And this should sound familiar to you because if you recall, when you first learned about is a solution saturated or not, you probably learned it in the context of how much of the solute can you dissolve? So what do we mean by that? Well, perhaps you are familiar with something like a simple syrup solution if you're a chef or you do any type of cooking, right? And so a simple syrup solution is made by taking a bunch of sugar, let's say a few, teaspoons of sugar, and adding just a little bit of water to it. Now, when you do that, you will in fact dissolve all of the sugar, right? But it's going to become this very viscous, hard to move around, almost like a syrup, right? Now, my guess is that if you continue to add more and more sugar to that simple syrup, at a certain point, the sugar will no longer dissolve in the water. And the reason for it, as I'm sure you can already figure out, is because you would have said that, well, the solution has now become saturated. So under our new context, what we're going to say is that once we added so much solute, we basically had achieved the equilibrium that exists between the sugar as a solid, right, as sucrose, versus the sugar on the other side that would have been in aqueous solution or dissolved. Because here's the reality of it. If you add enough solute to water, at a certain point you will saturate that solution. If the substance has, let's say, a very high molar solubility, so for example, sugar does a really good job of breaking up in water, right? The K value of that should be a huge value. But if I add enough sugar to water, eventually it does not dissolve. Likewise, I could take something like salt, right? I know that sodium chloride is great at breaking up in water. It's amazing at breaking up in water. But if I add enough of it to a water solution, eventually you expect to see the salt no longer able to dissolve. So all of these are examples of I added enough substance in, I added enough of the solute in, that at a certain point the solution became saturated. Or, to rephrase it, I added enough in such that my solution has now achieved equilibrium. Okay, so I think most of you can understand those two concepts. So what happens now when we take, going back to our insoluble salts, what happens when we have something that normally isn't very good at breaking up? Well, that just means that when you add just enough, you cause the solution to become saturated. And when a solution is saturated, we say that the solvent can no longer dissolve any more of the solute. Agreed? Another way to put that is that once we achieve equilibrium, the reaction quotient equals the equilibrium constant. Oh man, okay, so this is where we're going to pick up. So in order to help us understand what's occurring, let's take a look over here at this equation where calcium fluoride is dissociating. So remember what we said, that those halides were those tricky little exceptions, especially for fluorine. So fluorides, a lot of them tend to be quote unquote insoluble. What we see here is calcium fluoride is no exception to this rule. It is not very good at dissociating. Notice the KSP here is going to be ridiculously small. So at what point do we saturate a solution of calcium fluoride? In other words, at what point have we added so much of the ions in that no more of the solid will be able to disassociate? So really another way to ask this question is, when will a precipitate form? And this question of will a precipitate form is going to be fundamental when we're looking at KSP, because will a precipitate form is our clue as to whether the solution has become saturated or not. Now we're going to play with this idea quite a bit, but for now let's just kind of get an idea as to what we mean by, is a solution saturated or is a solution unsaturated? In other words, will a precipitate form or not? So let's come up with the following problem, or the following scenario. Let's suppose that we have a solution that contains initially, so at the starting point, you have 1 times 10 to the negative 4th of the calcium ion, and you have 1 times 10 to the negative 3rd of the fluoride ion. And the question would be, is this solution saturated? Or another way, hey, at this point, would we see a precipitate begin to form? Now, I gotta be honest with you. Right now, I'm not sure. I mean, these are small amounts, but the KSP is also a very small amount. Maybe I have too much already in there. Maybe I don't have enough. So as we said earlier, the only hope I have for answering this question is I must make a comparison between my reaction quotient and my equilibrium constant. So what do we mean? Well, we're gonna have to take a look and see if one of these statements is true. Is right now Q greater than K? If the answer is yes, that means that I have too much of my product. In other words, I have right now too much of my calcium ion and fluoride ion. And if I have too much of that, well, then that means that this reaction cannot make any more. And so when Q is greater than K, recall that we make our little Pac-Man, and Pac-Man's now going to chomp to the left, which means in this scenario, if Q is greater than K, that means that we're going to shift the reaction to the left-hand side, or we're going to produce the solid. We're going to precipitate out. If Q is greater than K, then the reaction is considered in this moment to be saturated. Period. End of story. Now, what's another possibility? Well, maybe when I compare Q to K, I find that Q is less than K. Huzzah! Well, wonderful. If Q is less than K, again, recall, we make our little Pac-Man. In this case, Pac-Man's eating to the right, or this reaction is going to shift more to the right, which means that we're going to make more ions. Or, say it a different way, there is the room to make more ions in the solution. Well, as long as Q is less than K, that means that the reaction is unsaturated. The solution is unsaturated. There still is room to make more of the ions in question. So Q is less than K, this is going to be an unsaturated solution, which of course leads us to the last possibility, which is, well, what happens if Q equals K? Now what? Well, when Q equals K, remember that means that we are at equilibrium, and as we stated earlier, a solution at equilibrium is considered to be saturated. So if Q is equal to K, we are saturated. Now, here's the trap question. Just because a solution is saturated, or rephrase, just because Q equals K, does that mean that for sure a precipitate is going to form? And technically, the answer is no. When you're right at that cusp, when you're exactly right at Q equals K, no precipitate forms because you're at that teeter-totter point. You're just there on that fine edge between I'm making products, I'm making reactants, right? I'm kind of flip-flopping back and forth. So when Q is equal to K, the solution is saturated, but as long as you don't put a single ion more in, we are not going to see a precipitate form. If you add more of the ions, then yes, from that point forward, everything starts to fall out as a precipitate. So, keeping this in mind, let's now take a look at what happens in this particular scenario. And so what we're going to do is that, as before, we need to write our equilibrium expression, except this time instead of an equilibrium expression, I'm going to make it a reaction quotient, right? Because I'm really more concerned about comparing Q. And what I know is that Q is going to equal the concentration of calcium ion times the concentration of fluoride ion, and again, this is going to be squared. Now, since we're solving for Q, I don't care about X and 2X and all that other stuff. We just need to figure out, does this have the ability to shift further to the right, or are we already saturated and that's as far as we're going to go? So I'm going to go ahead and plug in my initial quantities, and so I'm going to say that I have 1 times 10 to the negative fourth, and we're going to multiply that by 1 times 10 to the negative third. And of course, this is going to be squared. And when I do this, my new value of Q comes out to be 1 times 10 to the negative 10th. So, what does this tell me? Well, Q is a small value. But if I look at this, I'm going to say that right now, at 10 to the negative 10th, Q is less than K, which means that when I draw my Pac-Man is going to be chomping to the right. Or I can make more ions. Has this solution been saturated? And the answer is no. Currently, at this moment right now, the solution remains unsaturated. There is still some ions that could be added, and they would still be able to disassociate in my solution. Does that mean I have a lot of wiggle room left? And the answer is no, not really. My guess is a few more drops of calcium ion or a few more drops of fluoride ion will immediately cause Q to become equal to K. Now my solution's saturated. From here on out, all I'm doing is producing precipitate, precipitate, precipitate. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.